Okay. Today we are going to problem 3, 4, 5 in chapter 1. Problem 3. Using Dirac delta functions in the appropriate coordinates, express the following charge distributions as three-dimensional charge densities rho. Part A, in spherical coordinates, a charge Q uniformly distributed over a spherical shell of radius r. And first, we write down our charge density distributions form like this, and we integral over the space. We will get it has to be equal to total charge Q here, and the integration like this. This is our volume element, and the first term when doing the integration, it will give us r squared here, and this term give 2, value 2. This term gives value 2 pi, and the result will equals to a times 4 pi times r squared. And we will get our coefficient a equals to q over 4 pi r squared here. So the charge density distribution for part A will equals to this one. And next, part B, in cylindrical coordinates, a charge lambda per unit length uniformly distributed over a cylindrical surface of radius b. And the same, we write down our charge density distribution form and integral over the space, and we write in per length. So this term, this is our volume element, and the first term gives us b after integrating. This term gives us 2 pi, and we will get the result. Coefficient a equals to lambda over 2 pi b. So the charge density distribution will like this. And go next. Part C. In cylindrical coordinates, a charge Q spread uniformly over a flat circular disk of negligible thickness and radius r. And so we write down our charge density distribution like this, and this is the step function. It has a value 1 when x larger than 0, and it gives 0 if the x smaller than 0. So we just do following the same steps. This is our volume element. This term gives us 1. This term gives us 2 pi, and in this step we use the step function because we only have charge inside the radius r. So we integral our rho from 0 to r here after we using step function. And finally, the result equals to pi r squared times a. So our coefficient a equals to q over pi r squared. So we get the answer here. And next, part D. Part D, the same as part C, but using spherical coordinates. Okay, so here we write down our charge density distribution form, and the same we expand our volume into volume element and our rho. So, but here we have to notice that this term equals to the height. This is the volume's height. When our R goes up, the height will getting larger at the same time, but our charge density doesn't its thickness is negligible, so we have to do some adjust here to because our charge density doesn't grow when our R growing and the height growing here. So we should introduce the 1 over R here to cancel this R here. 就是呢，这一项在我们的 volume element 里面，它就像是高度一样的东西。可是呢，我们的 rho 它厚度是可忽略的。然后当我们的位置越远的时候，也就是我们的 R 越大的时候，我们的高度会越高。但是随着你高度的变大，我们框到的我们的 volume element 里面的电荷并不会随着你的高度变大而有所变多，所以针对这个情况呢，我们就必须要把高度上变化的 R 的这个变化，把它放在的 coefficient A 里面去做平衡，所以我们这里要导入一个 1 over R 的系数去消掉我们高度的变化。这种情况一般发生在就是因为我们是一个类似面电荷的东西，那随着你的体积的积分因子的就是它位置的变化，比如说我们在这里这个点，应该这样讲好了，我们是面电荷乘上面积，就是没有高度这件事情。那如果你的位置再近一点的时候，或是再远一点的时候，它乘上的高度是不一样的，就是我们的体积的因子，它乘上高度是不一样的。但是我们这个 xy 投影平面上的面积是一样的，所以我们在这一步的时候就必须要引入这个 1 over r， 这样子我们的那个式子才会是对的，就是从物理上的角度的话，因为Okay, so finally we get the answer. The coefficient A equals to Q over pi r squared, small r here. This small r is used to cancel the r coefficient in our height integral element. So the charge density here is just like this. And problem 3 is done. So we go next for problem 4. Problem 4. Each of 3 charged spheres of radius A one conducting, one having a uniform charge density within its volume, and one having a spherically symmetry charge density that varies radially as R in R of n order. R has to be larger than -3, has a total charge Q. Use Gauss's theorem to obtain the electric fields both inside and outside each sphere. Sketch the behavior of the fields as a function of radius for the two spheres, and for the third, with n equals to -2 and -2 and +2. For conducting spheres, inside the sphere, the E field has to be 0 because just no field inside the metal shell. Okay, shell. Sphere, metal ball. No E field inside the metal ball. So, and outside equals to Q over 4 pi epsilon 0 R squared here. And for uniform charge density, for uniform charge density, the rho function equals to Q over the volume, enclosed volume, for R smaller than A. And outside the sphere, the E field is the same as conducting. And for R smaller than A, inside the sphere, we should calculate the enclosed charge first. So here we are counting. No, here we use a Gaussian theorem, okay? And nothing. We just use our Gaussian theorem. So you'll get the answer here. And next, for spherically symmetric charge density, first we have to calculate out the coefficient C here, and just do the integral, and finally we will get the coefficient C here equals to this one, and the same the E field outside the sphere is the same as the conducting or uniform charge density. They are all the same outside the sphere. And inside the sphere, we following the same step. We use the Gauss theorem and calculating, and result is here. And for n equals to -2 and +2, we will get these two terms here. So for problem 4 is here. And next, for problem 5, the time averaged potential of a neutral hydrogen atom is given by following, where Q is the magnitude of the electronic charge and alpha -1 equals to A0/2, being the ball radius. Find the distribution of charge, both continuous and discrete. That will give this potential and interpret your result physically. So first we use Poisson equation, and we expand in spherical coordinates here. And we should notice that we have a look on our potential. Our potential will go when R approaching 0. Our value will explode. It will go infinity when R goes to 0. So we should be careful with our potential when the r equals to 0. So we divide it into two parts. The first part, when r larger than 0, is just do it normally. We don't need to notice anything. We just do it normally. We do the differential. We do the partial once and partial twice, and these 4 terms will cancel. Minus alpha, positive alpha, minus alpha square r, positive alpha square r, and finally the result equals to this one. And when our r approaching 0, we can't do the Laplace directly. We should first modify our potential. When r approach to 0, this term will equals to 1, and inside this term will goes to 0. So our potential will be modified into this term, this form. And this is the potential of a point charge Q at origin. So we have the point charge here. And hence the complete charge distribution will equals to Q Dirac R vector and subtract Q alpha in order of 3 over at pi exponential minus alpha r here. 其实就是如果你熟练的话，就是说Laplace r 分之一这件事情，就是当Laplace r 分之一这件事情，就是当我们的 r 趋近于0的时候， Laplace r 分之一会变得就是无限大，因为 r 分之一嘛。那点电荷给的电位就是 r 分之一嘛，所以就是可能从你以前电池的那些证明都有告诉你说，当你看到 Laplace r 分之一这件事情的时候，你就要特别小心，就是说它在提醒你有点电荷的出现，这样子。所以就是大家检查你的位能的时候要小心一点。Okay. So problem 5 is finished, and today we can take a break.